Hey everyone, welcome to Mr. Liang's chemistry mini class. Today, we're diving into the fascinating world of metal organic frameworks, MOFs for short. Sounds like something out of a sci-fi thriller, right? Don't worry, we'll break it all down step by step. Let's start with the classics. Metal oxide semiconductors like tin dioxide, tungsten trioxide, and zinc monoxide. These guys react when gas molecules in the air land on their surface, causing a change in electrical conductivity. It's kind of like our skin changing color depending on how we breathe. Pros: they're affordable, durable, and can handle a 200 degrees Celsius sauna session for 5 years straight without flinching. Cons: well, they can't tell who farted, give them methane, and they think it's carbon monoxide. Awkward. They're not exactly sensitive, they guzzle energy, and they constantly need to be heated, basically the electronics world's biggest diva. Now, making a grand entrance, carbon-based materials. Think Fast and Furious, and you've got graphene electrons shoot through it at 200,000 centimeters quadrat, vs faster than a bullet train. And carbon nanotubes? They are sleek, long, and packed with surface area, but left unchecked, they clump together like siblings fighting over Wi-Fi. Only with some chemical discipline can they play nice. Oh, and laser-induced graphene? Yeah, it sounds super futuristic, and it is, but it's still doing its lab internship. COFs built entirely from organic molecules with super strong bond scan, literally switch on and off under UV light. Total magic circle vibes. Some can detect ammonia in just 0.8 seconds. And now, spotlight on MOFs. Why all the hype? In one sentence: ultra, porous, super smart, lightning fast. Imagine MOFs as honeycomb hotels at the molecular level. Each molecule checks into its own fancy suite. Their surface area? Up to 7,000 square meters per gram. Yep, more than all the tiles in your house. The pores? Totally customizable from 0.3 to 4.8 nanometers, like molecular interior design, but make it nano. One standout: the ZIF 8 and PANI composite film can react in just 2 seconds. You don't even have to say hello, it already knows you're there. If only dating worked that fast. Here's a real-world wake-up call. In 2022, California's wildfire sensors failed to catch deadly hydrogen cyanide, HCN, which is fatal at just 50-100 ppm min. That failure put countless lives at risk. So, what went wrong? Traditional gas sensors, especially those based on metal oxide semiconductors, aren't great at telling gases apart. Tin dioxide, for example, reacts to way too many gases, making it nearly impossible to pinpoint HCN. Sensitivity? Not great either. Most commercial HCN sensors, electrochemical types especially, detect 1-5 ppm. But wildfires can release HCN at levels as low as 0.1 ppm, way below the detection limit, and 50 ppm can be deadly. Add in heat and humidity, wildfires can reach over 200 degrees Celsius, but most MOS sensors can't take more than 150 degrees Celsius. Throw in high humidity, and the electrolytes in electrochemical sensors can break down, causing resistance drift of up to plus-minus 30%. Not exactly reliable. Clearly, smarter, more selective sensing tech is needed, and this is where MOFs shine. They offer high precision, fast reactions, and much better gas discrimination. Now, how do we evaluate a gas sensor? There are 4 main indicators. First, sensitivity, how much the sensor signal, resistance, voltage, current shifts in response to a certain gas concentration, usually expressed as a ratio. Second, selectivity, how well it reacts to the target gas while ignoring others. Third, response and recovery time, how fast it reacts and resets, the faster, the better. Here are a few standout MOF examples that work well for wildfire detection. If you're curious, now might be a good time to hit pause and take a look. Still a bit puzzled about MOFs? No worries, up next, I'm bringing in some help. Let's check in with an expert. Hi, Chris. First off, could you explain what they are in simple terms?
Yeah, so a MOF MOF stands for Metal Organic Framework, and as in the name, framework means that you have a very ordered structure which is comprised of metal ions which are linked together by organic linker groups. So you have the metal parts, you have the organic parts, and then this builds up into a two-dimensional or a three-dimensional framework.
Have a porous sponge-like structure, but what sets them apart from other materials? And compared to traditional gas sensor materials like metal oxides, what unique advantages do MOFs bring to the table?
Right, yes, they're very highly porous materials, so they are quite like a sponge-like kind of structure. The sort of closest comparisons would be things like covalent organic frameworks, which are COFs. Those don't have the metal ion in them, they just have the kind of different organic regions. I guess what makes MOFs of interest is the ability to change both the metal and the linker. Means you can change the pore size, so you can change the size and the density of the pores in the MOFs, but you can also change the chemistry that takes place either at the metal or at the linker. So often you're interested in what they call host-guest interactions, which is where you host something like a gas inside the structure, and by having the ability to change both the metal and the linker, you can change the chemical interactions that can happen between your guest and your host framework.
What challenges are researchers still facing when using MOFs for gas detection?
Sensing, the sorts of gas sensing that we concentrate on in my group are what they call chemi-resistive. And what that means is the resistance of your material, the electronic properties, function as change as a function of the chemistry, so chemi-resistive. And because you're measuring the resistance, you have to have a conductive material. So of all the many MOFs that have been made over the last 20-30 years, not so many of them are conductive. And so that's the big challenge, is really finding appropriate conductive MOFs for use in gas sensing.
Thanks so much for your insight. Before we wrap up, is there anything else students or early researchers should know about MOFs?
About MOFs, I would just say the area has exploded over the last sort of 30 years, so that it's such a huge and diverse area now that it can be overwhelming. So it's good to have a clear idea of what part of MOFs that you want to look at. So we're lucky, we look at gas sensing of MOFs, which is a very, very, very small subset of all the work that's been done. So just have a very focused idea on which part of this very large area that you want to look at.
Okay, thank you.
Yeah, no worries.
After talking to the professor, we now have a better grasp of MOFs. Did you know that there are MOF-based gas sensors already working behind the scenes in everyday life? Here are 5 of the most common devices. Take the alcohol breath tester, for example. Its photo-activated MOF sensor uses UV light to oxidize ethanol, then detects alcohol levels through resistance changes. In example 4, the MIL101CR MOF detects nitrite in water via a fluorescence quenching effect. When the MOF changes color, you can compare it to a color card kind of like using pH test paper. Here is a quick roundup of MOFs' pros, cons, and areas for improvement. Thanks for sticking around for my first video. Got suggestions or questions? Feel free to reach out. I'd love to hear from you and make it even better.